On November 7, 1940, a suspension bridge began twisting apart in a wind of only 42 miles per hour. First, the roadway rose and fell. Then the motion changed. One edge climbed as the opposite edge dropped, twisting the 2,800-foot center span. Less than an hour later, the roadway was gone. This was not a hurricane. So what turned moving air into enough force to make a steel bridge destroy itself? 4 months earlier, the Tacoma Narrows Bridge had opened across Puget Sound. It linked Tacoma to the Kitsap Peninsula. When it opened on July 1, 1940, it looked elegant and light. Its 2,800-foot center span seemed to float. Its elegance concealed the problem. The roadway was unusually narrow, shallow, and flexible. Older suspension bridges used deep, open trusses. Those trusses added stiffness and let air pass through. Tacoma instead used shallow, solid plate girders. Those solid sides redirected wind, while the narrow deck resisted twisting. It could carry its expected traffic. Weight was not the problem. Strength against weight was not the same as stability in moving air. The most unsettling warning came before the bridge opened. Workers saw the roadway moving vertically in wind. Drivers watched cars ahead disappear behind rising roadway, then reappear as it fell. People called the bridge Galloping Gertie. Engineers knew enough to try cables and hydraulic dampers. Each time the bridge survived, the danger seemed routine. 4 months later, that assumption failed. On the collapse morning, side wind moved the roadway in vertical waves. The bridge had done this before. Shortly after 10 o'clock, the behavior changed. A cable band near midspan slipped, helping trigger the twisting. The edges began rotating oppositely. When one rose, the other fell. The deck no longer bent only vertically. It entered a torsional mode. The movement had become destructive. Every bridge flexes, steel bends, cables stretch, and decks move. Normally, damping removes energy until movement fades. Tacoma did the opposite. As the deck rotated, it changed the airflow. That airflow pushed the deck farther. The greater rotation changed the airflow again, adding force at a damaging point in the cycle. Instead of removing energy, the interaction added it. Rotation changed airflow. Airflow increased force. Force created more rotation. The cycle reinforced itself. The collapse is often called simple resonance. That explanation is incomplete. The wind was not merely delivering timed pushes at a matching frequency like a swing. More important was aeroelastic instability. Movement changed the airflow, which strengthened the movement. Engineers describe the primary mechanism as torsional flutter. The precise transition remains debated, but the bridge's movement helped create the destructive force. As the twisting increased, the roadway tilted at extreme angles. Concrete broke away. Steel connections and cables were pulled in opposite directions. At approximately 11 o'clock, major sections of the center span fell into Puget Sound. Within minutes, the roadway had disappeared, while the damaged towers remained standing. No human lives were lost, but the bridge was beyond repair. The collapse changed suspension bridge engineering. Designers could no longer treat wind as a minor static load. Bridge and air had to be studied as one system. Modern longspan design considers aerodynamic shape, torsional stiffness, damping, and wind tunnel testing. Open trusses let air pass through. Streamlined decks guide it around the roadway. Physical models and computer simulations test interactions before construction. Tacoma's failure became a design lesson for later bridges. A 42-mile-per-hour wind did not overpower Tacoma. The bridge's shape, flexibility, and airflow formed a feedback loop it could not stop. The failure proved that a structure can carry its expected weight and still be dynamically unstable. Its most dangerous force came from its own movement, growing with every cycle. This is inside the impossible. Engineering understood at the edge of failure.